Today we'll start with a brief overview of PMC, simulation tool categories, and a plant simulation versus Preactor chart. Then we'll present overviews of those two tools before taking questions. Kinematic tools like Siemens Tecnomatix RobCAD and Process Simulate Robotics let you analyze the real-time motion of robotic work cells, optimize cycle times, optimize welding sequences, and increase process quality. Ergonomic tools like JAC and Process Simulate Human let you analyze human motion and optimize the ergonomics of human operation to enhance worker efficiency and minimize injuries. Computer-aided engineering tools like NXCAE let you analyze specialized items like thermal and flow analysis and finite element analysis early in the design process. This results in better performing products. Computer-aided manufacturing tools like NXCAM let you analyze specialized items like tool design, NC programming, feature-based machining, and collision detection. This automates the development of molds, dies, and fixtures for higher quality, lower cost, and faster turnaround for machining. As opposed to the first four categories that focus on individual work cells or products, discrete event tools like Tecnomatix Plant Simulation let you analyze the operation of an entire department or facility and optimize overall items like throughput, buffer or inventory sizes, workers, and scheduling. Discrete event simulations are also referred to as throughput simulation. Although all these tools are really cool, the focus of today's webinar is on Tecnomatix Plant Simulation and also the scheduling tool called Preactor. Our next topic provides a handy comparison of Plant Sim versus Preactor. Our first question is, who uses it? Mainly plant engineers and managers use plant simulation, while production control teams use the Preactor scheduling tool. Usually, plant simulation is used on a longer-term scale during the design of a new facility or an update. The earlier the better here, while Preactor is used on a shorter time scale to make daily, weekly, or monthly operational decisions. Plant Sim's main display looks like the plant floor in either 2D or 3D, while Preactor uses Gantt charts, usage plots, tabular schedules, and internal web pages. Plant Sim models realistic stochastic processing fluctuations and downtimes that simulate randomness that occurs on the plant floor. In Preactor, fluctuations feed back directly to the scheduling engine. Plant Sim includes a genetic algorithms optimizer that can slash the time required to cover all what-if possibilities, like experimenting with the scheduling of parts. Now, unlike Plant Sim that requires time to run simulations for all the various scheduling options, Preactor uses specialized fast algorithms to optimize schedules. For bottleneck analysis, Plant Sim has a unique bottleneck analyzer that helps you to pinpoint bottlenecks. Also, traditional time and state charts and worker charts can also help identify bottlenecks, while Preactor has the ability to backward schedule to the bottleneck and forward schedule from it. What-ifs in Plant Sim include the ability to change inputs like schedule tables, cycle times, downtimes, setups, and buffer sizes. You can also add or delete equipment to see their effect on throughput, and an experiment manager lets you automate the what-ifs. On the other hand, Preactor lets you adjust schedules on screen with a very nice drag and drop interface. You can also add or subtract overtime hours, see the impact of new or rush orders, and reallocate resources. Plant Sim visualization includes the animation of parts and people moving through the model. This can help you to verify that the model represents reality and lets others see your facility in action, while Preactor reflects progress of jobs at workstations. Our next topic provides you with an overview of plant simulation. At this point, I'd like to point out that Tecnomatix plant simulation can model facilities other than just automotive-like assembly line plants. In fact, nearly any type of facility can be modeled, including those that produce tiny but important things like ball bearings, or large products like rockets, planes, trains, automobiles, tanks, ships, and construction equipment. Circuit boards, cell phones, containers, detergent, diapers, pretzels, candy, and my personal sweet tooth weakness, ice cream, as well as the facilities that process orders, package, store, and deliver these products. Even facilities where us humans are among the parts that move through a facility, like airports and hospitals. Tecnomatix Plant Simulation is a powerful software tool that allows you to create a digital model that simulates the operation of your existing or planned facility. The results of a simulation run let you analyze your facility, including throughput and location of bottlenecks. PlantSim's Experiment Manager that I mentioned briefly in a chart lets you automate what-if games, and genetic algorithms can help you to find an optimal solution even quicker. Lets you quickly show the bang for the buck of different improvement scenarios, or lack of it for other scenarios. Key features of PlantSim include object orientation, which provides intuitive use of powerful built-in and custom-made objects that lets you build models quicker. Hierarchy lets you structure complex models in an intuitive manner. It also makes it easier for you to make changes without having to tediously rearrange things like other flat structured products require. Last but not least, inheritance lets you make changes in one place. All children are changed accordingly. This ensures quality and saves you a lot of model building and updating time. As you can see, plant simulation can interface with nearly any other software product, including Team Center, databases, spreadsheets, and Factory CAD, even PLCs on the factory floor. PlantSim's analysis tools include a bottleneck analyzer that helps you to pinpoint bottlenecks. That's a real time saver. Sankey diagrams let you see the flow of material. The thicker the line, the greater the flow. This can help you to verify that the model accurately represents your facility and can help you to pinpoint potential problem areas and balance out the flow. As a user of PlantSim, I do that all the time, and it's very helpful. And finally, Gantt charts display resource utilization over time. PlantSim also has a very unique, powerful energy analyzer tool and reports that let you calculate and optimize energy usage. For example, the screenshot at the top is a section of a model that includes 6 workstations. Color-coded circles indicate energy usage, red the highest, purple in between, and blue the least. This makes it very easy to pinpoint areas to focus improvement on. The chart below shows the details of energy consumption. PlantSim's visualization options include 2D. This option is quick in 2 ways. Quick modeling time and quick simulation runtime. CAD integration lets you import a CAD file and use it to place modeling objects in exact locations. Some people prefer this, others prefer not having to place objects this way. The great thing is that plant simulation accommodates both types of users. A 3D view is optional, and this is getting more and more popular. And it's very easy to auto-generate and enhance. The great thing is that both 2D and 3D views are available, so you can take advantage of each one's strengths without being limited to one or the other as in other products. PlantSim also offers a unique optional view of your facility. Instead of the standard equipment view, the VSM library provides a value stream map view. This is great for those who prefer a VSM view. Plant simulation's benefits include enabling you to detect and eliminate problems, increase planning accuracy, optimize logistics and performance, and finally, PlantSim is the perfect tool to justify capital investments. Siemens a while ago surveyed 600 plant simulation users in approximately 200 companies. The results include a 12-to-1 average value-cost ratio. I've witnessed this kind of ROI in projects that I've been involved in. Our next topic is an overview of Preactor. Steve Weiss is going to be taking over. He's our resident Preactor expert.
Preactor overview. Let's talk about production scheduling challenges in general. Production scheduling presents inherent complexity. Any modern facility has multiple products that it's responsible to manufacture. There might be multiple possible routings per product because workstations back one another up or cycle in parallel. The various products at various stations have cycle times and curing times that vary. If we're talking about food or certain substances, expiry times. They can't wait too long between processes. And then, of course, as we move through a product mix, there are varying setups and teardowns and cleanouts, which themselves take varying amounts of time and or the attention of certain specialists, specialized operators in the plant. Now, if that weren't bad enough, there's external contingencies because product mix demand can change. It can change moderately over time, or it can change very quickly if there are a number of rush orders. Product volume demand can change, sometimes in a known seasonal pattern, sometimes not necessarily. And then there can be material shortages. It's a just-in-time world, but sometimes that material doesn't arrive just in time, so the production control team needs to be able to respond to that. And then finally, as much as we'd like to be fully in control of what's happening inside the facility, we're not. There are internal contingencies such as equipment breakdown. You can have a lean staffing level in which one or two absences suddenly means that a department or part of a department is going to go offline for a day or a shift. Some scrap may take place, and we may have calculated the amount of scrap to occur at a given workstation, but you know that number is almost always a distribution, and it's high end. It's an internal contingency that we have to deal with. You know, some mistakes or errors don't have to be thrown up, they have to be reworked. This means they cycle back through the system. So there's tremendous complexity involved in production scheduling, and that's why the operational solution is advanced production scheduling. And again, this is an operational solution as opposed to a method of design and planning, which simulation makes available, which PlantSim makes possible. And the main components of advanced production scheduling system are, first, the scheduling engine itself. The scheduling engine at its very base function must deal with that inherent complexity. It must be able to understand there are different products that have different routes, that as they move through the plant, they have different cycle times. It must be able to accept those orders and provide work instructions for those who are going to build to them. Now, in order to do this, it needs to be able to respond to the external contingencies that become known typically through the ERP system, the orders, the order amendments. Also, you see here material availability. From a production control standpoint, you don't want to have to think about this. You want to believe that all your material is available when you need it, but sometimes it isn't. Sometimes you have those shortages. That has to feed into the scheduling engine. And what is handy as we look at that blue arrow on the right is for a scheduling engine to be able to feed back to the ERP system, so that the marketing and sales people in particular who are in contact with customers, so that your customer support team can say to your customers with assurance, yes, this work is in progress, or no, it's not in progress, but it will start tomorrow, it will complete on Thursday, ship on Friday, you should have it on Monday. So that takes care of 2/3 of the picture, but then there's also your internal contingencies, typically reflected in your MES manufacturing execution system or SCADA system, because not everything works to plan. The scheduling engine is, now we start with the arrow on the right, going to pass that schedule, going to pass those work instructions down to the shop floor, but not everything may be built to plan on schedule due to breakdowns, due to unexpectedly long cycle times caused by variation in raw material. So this information needs to feed back, blue arrow on the lower left, this order progress needs to feed back to the scheduling engine so that the production control team at the end of one day and the start of the next can say, okay, how did our plan match up to reality? So you've got to have a really strong software package in the middle there and strong integration with the systems above and below it to implement advanced production scheduling in an optimum way. When you've done that, that tool provides a lot of benefits as an optimization tool, defining strong baseline schedules, as we said, inherent complexity. It works as a communication tool, publishing schedules and processing feedback. It works as a decision support tool to help the production control team respond rationally to fluctuations. And I want to emphasize two things in the middle here, because there's a little bit that's unexpected. One of the benefits we often see when we implement an advanced production scheduling system is that we regularize the flow of information. Sometimes, the inherent scheduling isn't that difficult. What's difficult is distributing the knowledge around the plant of what's going on when. By putting the scheduling engine and the scheduling system at the center of a defined process, what that means is everyone can see at a glance what's going right, what's going wrong, and therefore they can manage by exception. And what we've seen is we often really streamline communication so that less time is wasted with people asking one another, where is this order? What's happening in the lamination department? They know, and once they know, they can flag those things that aren't quite right, and they can manage by this exception. And that goes into an APS system's role as a decision support tool. It's very smart. Ultimately, it's not going to replace the production control team. It's going to help them make better decisions. It's going to help them understand, okay, this is the current global state of the system. Here now I can do some what-ifs to understand the ramifications of dealing with it in this particular way or that particular way, to respond rationally to fluctuations. A decision support tool, not a decision co-opting, a decision taking over tool. But when it's all in place, when the optimization and the communication, the decision support are in place, we get to the bottom line that APS is a profitability tool that helps maximize throughput and minimize costs throughout the facility. Here at PMC, we have chosen to promote, to resell, to configure Preactor because we see it as the best-in-class APS solution. It is offered by Siemens. It produces Gantt charts and plots and other outputs that allow the production control team, that allow the scheduler to understand what the baseline schedule is, to make modifications to that baseline schedule, and then ultimately, when it's ready, and that process could take 3 minutes or 30 minutes, or in the case of a particularly difficult scheduling challenge, 3 hours, when ready, to publish work instructions to the floor that either go directly to the operators or go to supervisors that can then distribute them to the operators. So everyone is singing from the same songbook. We chose Preactor, and we promote Preactor, and we recommend Preactor because it is a world leader in advanced production scheduling systems. It has a global footprint and a multi-sector footprint serving manufacturing across the globe, ranging from mid-sized companies to some of the largest multinational companies in the world. And because it operates across multiple sectors, it has the flexibility to solve any scheduling requirement, and we've got the case studies to back that up, no matter what industry you're in or what part of the world you're calling from. What I'd like to do now is recap PlantSim as opposed to Preactor. And again, who uses it? Plant engineers and managers in the case of plant simulation. In the case of Preactor, production control teams. When PlantSim is going to be used, typically in the design of a new facility or an update to a facility or an update to process, these are decisions that can be made on the longer time scale. But operationally, we don't have the luxury of a longer time scale. And on a shorter time scale, making those daily, weekly, monthly operational decisions, we're going to use Preactor. Now, plant simulation has the benefit of really creating displays that look like the plant floor, either in a 2D or 3D projection. Preactor is less interested in representing the plant floor literally and pictorially than it is in presenting Gantt charts, usage plots, tabular schedules. Also, by the way, internal web pages. When we talk about publishing a schedule, it's not necessarily a bunch of sheets of paper that come off a printer. We can push the schedules to the website so everyone can see it from their monitors on the shop floor. One thing that plant simulation does pretty well is it simulates realistically the stochastic fluctuations in processing times and downtimes. In Preactor's case, we deal with those, but not by simulating, not by anticipating what they might be, but by seeing those fluctuations feedback directly to the scheduling engines. PlantSim optimizers use genetic algorithms to reduce the number of what-ifs to consider, whereas Preactor algorithms help optimize schedule more or less on the first pass. With plant simulation, you analyze and identify bottlenecks using time and state charts and workers charts. That will help you pinpoint bottlenecks in your process. Once those bottlenecks are known, then Preactor, as one of its algorithms and one of its optimization methods, is to configure a model that backward schedules production flow to the model deck and forward schedules from it. So here in plant simulation, we identify the bottleneck, and then knowing that, we alter our operations accordingly. There are a number of ways to do what-ifs in plant simulation, and in terms of changing, a number of parameters to the existing equipment, such as cycle times and downtimes, in terms of changing the equipment that might be installed in the hypothetical new facility or modified department. In the case of Preactor, the equipment, the amount of equipment, the parameters of the equipment are known and decided. Where the what-ifs come into play is when the scheduler uses drag and drop capability to adjust the timing and the routing of specific orders, to measure the impact of new or rush orders before they're sent to the floor and to reallocate existing resources. Plant simulation really can do visualization more or less as a highly viewable animation. We don't, in Preactor, we don't animate the flow of material through the facility, but we do dynamically update the known progress of jobs at workstations, and those can be reflected in a number of ways, as shading on the bars of Gantt charts, as percentages on tables next to the list of operations in progress and operations to be performed. So these each have parallels to one another, and ultimately this all adds up to a really, really strong pair of best-in-class tools provided by Siemens and configured by PMC to give you and your facility the best chance of success and the highest levels of uptime, throughput, and profitability.